name is Velmir Fleischmann. I'm a mechanical engineer. I've been working with simulation for more than 15 years with different softwares, for example, ANSYS, Abacus, Permas, LS-DYNA, SolidWorks, and also with optimization, for example, Tosca and Virtual.PYXIS, which is our software. Currently, I'm engineering and business manager at Virtual.PYXIS.
Senão eu te mando aí.
So, Virtual.PYXIS is a topology optimization software. The idea is that the software is able to handle from simple to complex optimization situations. What I mean here, complex situations, is because we can take care about nonlinearities, for example, material and contact, here running with friction or any variation of friction. Compliant mechanisms, which is a flexible mechanism. I have an example here to show a little bit more about this. And multiphysics analysis. Software has a very modern algorithm optimization, so we can guarantee a nice optimal result, which is less weight as possible and keeping the stiffness as much higher as possible. Virtual.PYXIS is a software independent optimizer, which is we are completely open. Even the fact today we have a relationship with Abacus and ANSYS solvers. The relationship, I mean, we can read these two solvers. We are kind of solver independent, so also some other solvers we can add for the optimizer without depending just for one solver. Where the places we have been working, this is the slide I show you. For example, we have an office here in Chicago, US, the place where I am. Also, we have an office in Hanover, Germany, and a relationship with Virtual CA in Brazil, which is our subsidiary in South America. So here in Hanover, our office is in a place called Wissenschaft Park, which is a technology park. And Chicago is inside the Illinois Institute of Technology and also a technology park. We are also an ANSYS partner, so later I will send this presentation to you, which is not confidential. If you go to the ANSYS website, you see under software partners that we are developing something that ANSYS recognizes, something which gives value to the ANSYS. So we are partner of this development together. So just here, talk a little bit about the main advantages of the software. In this case, I just the presentation here today, I'm focused more on ANSYS, so that's why I say just ANSYS. In this case, we use ANSYS solver during optimization cycles. What does it mean? Like, for example, for the optimization, you get, for example, 20, 30 interactions, and for every iteration like this, we use the ANSYS for the solution. So our optimizer just take the results of ANSYS, like for example the strain energy, and try to optimize this from every iteration, every step, every loop of the analysis. So we also take advantage of many different kinds of analysis. For example, linear, static, frequency, nonlinear situations also involving geometric, material, and friction contact. Filtering techniques is something also important during the optimization. And here we have a very also modern methodologies for this. For example, projection, heaviside methods. Today I'm not going very deep about every detail of the theory, but if you have some questions, I can answer you today or another time. So manufacturing constraints also something I can tell you that most of the situations, for example, casting or plastic injection, we can deal with that, which is important for optimizer. If not, you are not able to manufacture your product after the optimization. It's a unique solution for a combined mechanism. We, as I told you before, I have an example to show what does it mean, but it's a very complex analysis, also involving some nonlinear constraints of the optimization. It's a very complex analysis, and also modal pre-stress, and which is more or less, I'm talking here about the integration between two areas like structure and static structure and vibration, but also something that can generate some mechanical strain to be used for a structural optimization. For example, some thermal load which generates some expansion of your model generated mechanical strain, and after that I use this mechanical strain to optimize the model, which is very nice to talk about the ANSYS, because with ANSYS the software is very known about this possibility of multi-physics situation. Here is just an overview about the design workflow. The pre-processing of the model can be done in ANSYS or even Abacus. Here is an example of the ANSYS window. I have two workshop models I will show you today, so you will see a little bit more about this. And here our developed partner is ANSYS in Brazil. They are have been working very much with ANSYS for a long time. Solver interfaces ANSYS and Abacus. So the solver for the optimizer is not from our side; it's from ANSYS and Abacus. We just take care of the result of every interaction, which is important and good to say, because we take advantage of the best thing you can have from your solver. There's no limitation. You use most of the features from ANSYS and Abacus during the optimization cycle. And also post-processing we can have for example, peer review and ANSYS also, and hyperview. But post-processing is the fact you want to have, for example, the smoothing of the surface. So at the end of the optimization, you'll see, for example, some parts of the model that has to be kept, and some parts that can be get out of your model. So what this post-processing really does is taking all the parts which are not important to your model and smooth the surface. And after that, with, for example, this STL file, you can go again to your CAD and you can prepare the final model based on this smoothed surface. So here just some models just to understand a little bit more the applications of the software. Everything I show here is not confidential, so just to understand a little bit more. So here is a Cummins model. It's a truck engine mount support. It's nice because when you start the optimization, you go from this extended design and you get something like this at the end, also with the validation. And I'm talking here about 23% of weight reduction. The result of the topology optimization itself is like this one. And after that, of course, you have to go to the CAD again. And there are some ways to try to get shorter time to prepare from this part to this part today. Like for example, in ANSYS to this version 16, we have a model called SpaceClan, and this SpaceClan is a software now is part of the ANSYS, and the idea of this software, which is a CAD software, but preparation for the simulation, and also post-processing, in this case, like for topology optimization. So SpaceClan take this model and try to get as soon as possible the final model, join some surfaces and repair some corners of your models. So it's a very nice tool, trying to reduce, because most of the time the people are complaining to get this result to the CAD interpretation as a final result. Also here, just this is a different phrase for example, gear model, and here we show something like for symmetry, in this case rotation, symmetry, and extrusion, using pattern design, pattern repetition around the model, and here using polymer, which is most of the time we think it just like for example cast some steel or some aluminum can be optimized. It depends. It can also take care of like for example injection injection model. In this case we are talking about polymer. Sorry. Here we are working with all the loads which normally they are acting for this gear. And this is the final design with 35% compared to the baseline model. Here's also a nice example from AGCO. We worked together. So this is we are taking care about the nonlinearity of the situation, because this is analysis of ropes, which is the rollover simulation of this structure. So this support comes here, in the front part. So we start from this, and we get this. And the idea is try to get something like a homogeneous reactions of all both loads. So that's important. For example, optimization, and we think most of the time you are talking about just weight reduction. But in this case, like for example, this is the original model. From this model to the optimized model, also we have more weight here. But with the optimization, we can distribute in a better way all the reaction for all both loads, which is like for example good for the attachment between this support to the transmission, which goes this part. So it's not like, for example, most of the time just talk about weight reduction, but also solving some specific problem or something that can be very difficult to design by ourselves, even if you are expert designers or engineers. And also here it's important to say it's some controlling that we have during the optimization. We can use also, for example, this is for plates and welding plates. So there's a control of the thickness, because most of the time also we are thinking that when I'm talking about optimization, can just work with, for example, plastic, polymer injection or casting. So here is an example of welding and welding plates with constant thickness for these two parts, like this. So here also a nice example from ThyssenKrupp. This is a model called pinless project, which is there is no pin on this assembly, just the con rod and the piston. And in this case, we would like to control the situation. Most important in this case for optimization, of course, there's compression and tension, but the tension load tries for example to displace this part to the left and also this part to the left, to the right, and also this part to the right. So because they are trying to separate each other from the tension load, like go up and go down, the piston and core rod. So after, what they did here after the optimization with this new structure, it also works as a flexible mechanism. After or during the tension load, this part, instead of going to the right, it goes to the left. So solve this problem because there's a cylinder here, and if you go this part to the right, it can be a very huge problem about failure or something like that. So this is a important model also talk about optimization. So now I have some models to work with in ANSYS. So the first model is for a nonlinear static analysis. This is a kind of model which is more or less with the same size as a real model, more or less the same loads as a real model. So here we have an assembly of a con rod and cap. Here there's a pin. Here is the bearing, and also here inside there's some screws which are tying together the cap and the con rod. So just to have an overview about this model, here we have the contact. For example, the contact as a friction model. We are working here with 0.1 for the friction coefficient from con rod to pin. Also, there's a contact. Everything is here is friction, just to summarize, using also every time 0.1 for friction coefficient. In this case, we are using the contact in between con rod and bearing. There's also contact in bearing and cap. Contact in between cap and the con rod to prevent anything that happens in between these two parts. There's also a contact in this part, this case. For example, the screw to the con rod and the screw to the cap internally to this part to prevent the approximation of the head of the screw against the surface. So here is just to show about the mesh of the model. This can be used. There is no restriction in ANSYS or even perhaps in Abacus for the elements. Most elements you are using during your structural analysis can be used here. Even there are tetra or hexaedra elements or first order or second order. For the optimization is the same idea as you are using for a normal simulation or a standard simulation. As more elements more elements you have, the better. And also, if you work with nonlinear or second order elements, also you get better optimization results. So here in this case we have a situation of 3 load steps. So the first load step is the case we apply both the pretension of your structure for both sides, and in the next steps you apply here, for example, traction and compression loads. So this case is compression, and this case is traction load, and all the time applying in the pin, which is more or less represents the contact in between pin and the piston. So here for compression, top part, and this part for traction load. So here also there's sometimes as the mesh is not 100% symmetric from both sides, and also sometimes try to get an easier convergence of their model. In this case, as a symmetric model, we are just emphasizing the symmetry by controlling the displacement of the surface, which is outside surface, which is more or less divided the part in both parts from this plane and also from this plane. But this is more than the optimization. Is for more controlling the convergence of your nonlinear static model. And here we can see the results. For example, the pre-stress, which is giving a higher stress on this region of the pretension. And also, for example, here you see the deformation in some scale. In this case, we are using more or less 100 times more to see how it works for the traction and how it works for the compression situation. And also here, for example, the stress and for traction and the stress for compression. So from here, now I can prepare the optimization model. So when you are using, in this case, for example, our software, you have just to go to the ANSYS as perhaps who is working more with the ANSYS ACT, which is the ANSYS customization tool. You have just install your extension. You have some extension, a standard extension for that. And after that, you just manage this extension, which is our case like here, Virtual.PYXIS. When I check this part, you see here the optimization option. So you just go to drop this to your model analysis. And so, for example, here inside the ANSYS tree, now you see the preparation of your optimization. So, for example, one recommendation that we normally give is for example, we see the element size of the part which you are trying to optimize. In here, we are enforcing 3 millimeters as element size. So, for example, in this case, you used to recommend 2 times as a minimal member or minimal radius for the optimization creation. Like, for example, the software, you control these minimal members as 2 times of the element size. And also here you can see more possibilities of material law, filtering techniques, and some more controlling. We have some documentation. Everything is well explained in that. And something important when you are running the optimization. For example, here we can also use pair review, as I showed you before, as a post-processor model. You can also export the STL model here inside the ANSYS. So we take the last result of the optimization, create this STL model inside the directory that you are running. And also you can use this MPI license of ANSYS. So this is not the parallel processing of the optimization, but this is the parallel processing of ANSYS in this case. So as we are taking sometimes 20, 30, or 40 interactions, the time for the optimization is more or less 1%, or sometimes just a little bit more than this. So most of the time, in this case, is ANSYS processing, and with this ANSYS parallel processing, we can speed up the solution using, in this case, 4 processors. So you see that's a very simple preparation of the optimization. In this case, we give the software which geometry we are really want to optimize. In this case, we call the design entities. Here is the menu for optimization. And also, in this case, you want to control, for example, the volume of your structure. Here, using, for example, the static structure analysis we have done before. And less or equal, for example, I want to reduce 65%. So I'm meaning that I want to keep 35% of the optimizing model compared to the initial model. So this is the part of optimized model you have just 35% of the initial model. Again, for these two, on-road and cap. So in this case, I need to create a load combination because if you go back to the loaded history, so the first load step is the bolt pretension, and the second and third load step are related to traction and compression loads. So what we do here, we create, for example, two lines, and we call, for example, as a second step, which is the traction, we can have, for example, wave. Wave here is not related to the structure, but the wave of the strain energy for the load step, second load step, and the third load step. So here you can combine as many as load steps you have, and it's important because, like for example, in this case, the compression and traction loads, they produce different strain energy of your model, and they are not acting at the same time. So, for example, if the loads are acting at the same time, you don't need to have two lines here. You have just one. But here you are talking about different load steps, different times. So we have to create this load combination. So the optimizer will see about the result of the traction, the result in compression, and we'll try to get the best design in between these two results. So after that, now the last part is the objective. In this case, I want to minimize the compliance of my model. So for example, when I say that I want to minimize my compliance, is like the same way I'm saying I want to maximize my stiffness. So this is more or less the same way to say. And here again, I control which situation I have here. This is the static structure. Again, the geometries of the model. And here now I can call not the single load, which is, for example, for just one load step, but the combination I have just created some step before. Just to go a little bit more in detail about the constraint, here I also the constrain the volume, but also here you can go, for example, to control more things, and also for manufacturing constraint. For example, casting constraint, you can prevent some opening direction, and also more things about the procedure itself for the manufacturer. So everything also can be controlled here under the constraint. In this case, they are not volume but manufacturing constraint. So if everything is fine, for example, here I can start the solution. So now you see that the optimizer will call ANSYS, running ANSYS, and also calling the MPI license for this case. So when I go to the task manager of my model, so here you see, for example, some ANSYS procedure is running during the analysis. So it takes some time for solving this model. I have prepared here final result for this situation. So after we get that solution, you just go here to the node and element density plotting, And for example, in this case, I'm plotting the node results, so you can have a look from a nice view from your model. For example, what you have in the beginning and what you have at the end. So it's a brand different situation, and here the software tries to keep as much as possible material from pressure on both sides here, and also there's some material around the screw, because there are also some energy that are accumulating here. So it's a nice situation for the results, for example. And also here you could also use this STL, which is inside the directory of ANSYS, to be, as I told you before during the presentation, use it to go to the CAD and try to have this part as another model. Here is also nice what we see here, because most of the energy are not in the middle of this upper part of the core rod, but in places of the contact, so that it gives some different results. So here you can see some material which is removed, and this case also could be controlled by, for example, using casting on Z direction to prevent, like, for example, to have this this material going to the deep, like here. Yes. So, for example, here, now I have another model which is taking care about, just a moment, I have some questions here, and I try to answer as soon as possible with the help of my friends at the end. So please continue sending me these questions. We thank you very much. So now I will show a different model. As I told you, it's for a frequency situation. This is a model from Cummins, which is not non-confidential model. We can use it to show it. And here, just to have an overview about what we did, the first, let me just show you here. So by the ANSYS integration model or project, we have here the static structure analysis for generating the pretension of the bolts. And after that, use it from a model analysis, the result from this pretension static structure to optimize the vibration situation. So when you go back to the tree, you see like here the static structure, and the model analysis calling the static structure. So why is it important? So sometimes you see when you're using for example, some structures that you have this pretension or loads acting during the static analysis, you see that there is some difference when you compare the results of the model analysis. So, for example, here the pretension can add some additional stiffness to your model. So, if you don't consider this stiffness, you can perhaps sometimes try to optimize the vibration, but in a different eigenvalue. For example, without pretension, you have, for example, 100 Hz. With pretension, you go sometimes a value different from 100 Hz because you have a pretension structure, and if you change the stiffness, also you change the overall stiffness, change also the overall eigenvalue, which is the value of the frequency of the model. So it's important sometimes to consider this pre-stress model, and there's no limitation in our case. So just to have an overview of the model, here we have just restrictions for this part which represents the cylinder, the engine block. We have here 4 pretensions for all both loads. So here the values are more or less, it's not like this, we're just changing the values. And also here I have, for example, a point mass. In this case, we are using 10 kilos to represent, like, for example, unbalanced mass from connecting to this part. So the idea here is, as I told you before, to have in the first analysis the static having the pretension of the structure, and after that we are trying to optimize the vibration modes of this part as an extended design to get the best result for the optimization. So when you see here the results of the static pre-stressed, so you see some stress around these screws and also some deformation. And after that you have for example, the vibration modes. And the first vibration mode is trying to move up and down this part, and other vibration modes for bending and torsion modes. So going back to the tree, in this case, we start a new topology optimization analysis. So now you see here, in this case, if, for example, just want to see which element size we are using. In this case, we have 5 millimeters for the support. So here we use, like, for example, 2 times 10 millimeters for the minimum member size. As I showed you before, also you can control, for example, the STL generation, parallel processing of ANSYS, for example. Design entities, in this case, again, the support. For example, I want to control the first constraint, the volume of my model, as a fraction of the model situation, and less or equal. In this case, for example, just an example of 35% of the final result having 35% of the initial model. For this part, again. So now you can go to the objective part. In this case, different from the first model we ran. This is for control of the model situation. Here you can see the model analysis. And the objective is different from the first example. There we try to minimize the compliance. Now we are going to maximize the frequency of my model, because it's more important for vibration maximize than most of the time minimize the frequency for this geometry. And now I can control, for example, which frequency I want to use. I see 6 here because it was also from the analysis settings of the model analysis that I'm plotting 6 modes for my case. It can be more than 6, 10, or 15. And also here, I can try to prevent sometimes, we call this mode tracking. Like, for example, when the modes are trying to cross each other. So in this case, what you have to do is, again, to create a load combination. Line by line, you have to call, like, for example, first, second, third mode. And here, instead of using the single load step, use the combination. So you try to see not just the first mode, this part going up and down, but also other modes that perhaps can affect, like, for example, the second mode, vibration becoming the first mode, and the first mode become the second mode, like this mode in crossing. So, like, for example, here everything's fine. You can, again, just start the solution and try to get less time. Here I see some results that we have. The mesh is not very fine to get a nice result, but here you can see a tendency of your model. And what we recommend most of the time, for example, you don't use any manufacturing constraint for the first result as we have here, and you see what's the tendency of your model. For example, which situation I can use it better for the manufacturing controlling. We have a lot of papers and materials, and later we can share with you if you want. Like for example, comparing the situation I don't have any manufacturing, and in how is the influence on the results. Talk about, for example, frequency or stiffness. And this is the first situation. The second situation, you try to enforce some manufacturing, like for example, going to this direction onto the top. So again, you can control this. It's not a problem, but it's recommended for every time during the optimization, you try to get first without any manufacturing constraint. After that, you try to match the best design that you are getting to the manufacturing. So here is, as I told you, the final result. Let me see, I can have here more or less the objection function. In this case, we are maximizing the eigenvalue or the value of the frequency of my model. So this is the first mode going up to this part. So you can also have some plotting to get a better understanding of your model. Yes, I think this is everything that I would like to say you. This is just the last part. Here is some contacts that you can try to reach us to get some material, some more information. You are completely open for any request. You can take my email or you can call me here. But anyway, I will send this presentation to you later, and you can have this contact. So now we can have some minutes trying to answer some questions. I suppose that I try to answer as much as possible. So let's go to the beginning here. Just take some time to try to read here and try to answer you. There's a question from Thomas, which is asking what is the nonlinearity of this model. I think he is talking about this first situation. So about the nonlinearity, you have many situations. For example, load nonlinearity, which you, for example, applying loads step by step in different load steps. Or you have, like, for example, geometry nonlinearity, when your geometry goes very, you have a lot of deformation. You have material nonlinearity, and also you have a part of the analysis which is called contact nonlinearity. So in this case, we are using the contact nonlinearity because it's a friction contact. So when you go to the convergence, like for example, you see by Newton-Raphson convergence, that the model is going to a nonlinear situation of result. So that's the answer for this. This is a nonlinear contact model. Yes, also can be the friction, the pretension can be as a load step, because there is both nonlinear contact and nonlinear about load, because we created 3 load steps. First, screw pretension, second, contraction, and third, the compression. Let me see what we have more here. Yes, there's a question from Ellie. How do you can extract the result geometry? So, for example, there's 2 ways you can get the final result from, for example, this result, like this one. there's a when you run the ANSYS analysis, you have a structure of files and directories. So when you give the software the possibility to say yes here, for example, to yes STL file, when you go to these directories, you see a lot of files, and also you see the STL file of the final result like this one. This is one way, so it's inside the ANSYS, but you can also use ParaView to complete this situation. For example, let me take this part, like for example this one. So ParaView is an open source and free code, and it's very powerful. I have been using very much this software. It's very powerful for optimization, and we created some routines inside here to apply the geometry to get this smooth surface. So for example, here you go to the last step, and you create some filters. For example, I'm using this case, for example, 0.3 for filtering of the result. So you see more or less what we are seeing in ANSYS. So from ANSYS you get the STL directory from the directory structure, and here from ParaView you have just to go, for example, save data, and here you can export the STL format of this final result. So as a CAD user, for example, you can go, you can take this STL result and go to SolidWorks or Inventor or every software used for CAD and try to rebuild this as a final result, or even Space Client from ANSYS, which is a very nice tool. It's an add-on model. You can add it is integrated to the ANSYS Workbench project also, and you can take the results from this to a better understanding of your model. There's also a question how the optimizers communicate with ANSYS solver. Yes, for example, in this case, everything runs from the batch. Like for example, in this case, I'm still running the model. So we prepare everything here with the ANSYS tree. So that's nice because you don't really need to know a new software GUI. You just to understand a little bit better how is the preparation of the optimization. But after preparing this situation, we run the software, and ANSYS will take for every condition. There is a kind of automatic batching analysis, which is for every interaction we are running ANSYS and get the results to the Virtual.PYXIS after that going back to ANSYS. So everything is automatic. There's no much work to be done here. It's just to see the result after that with the user. So, but again, it's like a kind of loop. Virtual.PYXIS working together with ANSYS and calling like this window in batch. Most of the people are asking about some paper also. For sure I can share with you. Ellie is also asking about the difference between max, min, and KS, max, min. So I will try to get our developer here. I think you answer in a better way. So just keep this last question, Ellie. I will try to answer you. here also my people, they are helping you. The KS is the Kaiser-Mauer-Steinhausen function. It's a kind of explanation, formulation of your model, it's a specific situation, trying to get a better solution when you see that your modes, they are crossing each other. So when to go to objective function, and if you see there's a possibility of crossing modes, you can use this KS to prevent this crossing mode, which is the Kaiser-Mauer-Steinhausen function in explanation formulation. Yes, we can use, for example, high performance computing here. There's no problem. We can use a space clan as a space clan. You can, for example, we can get the STL result from ANSYS or from by generating ParaView, and after that we can use a space clan. Unfortunately, I don't have this model, but for sure we will try to prepare a new WebEx because this is brand new for space clan version 16, and we will try to show you this situation and how to create this in a better way, these results to a better CAD model. And so the answer is we are getting the space clan is getting the STL result. Ellie is also asking about the checkerboard. Ellie, you address this answer to our developers? For sure, they will answer you in a better way. Also, Jeremy is asking about if it's possible to prepare a batch locally and send it to the server. Yes, I think I also have to give this information to the development team, but I'm sure there is no problem about this. So people, I think more or less everything is here. I try to get these questions that I am not answer here. I will send for everyone. And from this time, I really want to thank you for joining us here for this WebEx. And I suppose that it was a nice opportunity for me, also for you to understand a little bit more on what we can do with topology optimization. So thank you very much. I don't like to extend very much because there are some people in South America. I think it is lunchtime now. And really thank you. I'll send this presentation and you keep in contact. If I didn't answer any additional question, as I told you, try to answer. If not, please send me one email and we address this answer. Thank you very much. Bye-bye.